Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. We are with chapter 4 of microwave engineering, the transferred electron devices we have started with. After learning the microwave tubes, working on to the principle of velocity modulation, we have shifted to the negative resistance principle of working so that we can generate the microwaves. So we initially started to learn the Gunn effect, the Gunn effect diodes we are introduced to. Now the very important topic that we are going to address here, that is Ridley Watkins Hilsum, called as RWH theory, which is also referred to as two-valley model, we shall be discussing in this video. So let us start. So here we start with our topic. Our topic is Ridley Watkins Hilsum RWH theory. As the title of our chapter is Transferred Electron Devices, and in this particular family of devices, the most popular is Gunn diode, invented by J.B. Gunn in the year 1963, we can say. So as there it is a transfer of electron from one level to another level. So that can be better explained with the help of the model that has been given by Ridley Watkins Hilsum RWH theory. So up till now we have gone through the understanding that the Gunn device, the Gunn diode, is a bulk device. There it is no junction and it is made up of a semiconductor compound, either gallium arsenide, indium phosphide or cadmium telluride. So to this bulk device we are providing a DC potential so that the electric field will be generated across the bulk from one terminal to another terminal, and it is observation that after the threshold value that we have formulated into the previous video as per the findings of J.B. Gunn, the device is supposed to exhibit the oscillations. So those particular diagrams also we have been explained with. Now let us discuss first of all, before starting, exactly the two-valley model, that is differential negative resistance. So to understand differential negative resistance, we can have the two modes of operation. Let us have them. So here, the very first of all, onto the left hand side we can take a voltage controlled mode, and onto the right hand side we shall be taking a current controlled mode. So now to represent the voltage control mode and current control mode, we take the help of the two axes, one horizontal and one vertical here. Onto the horizontal axis, we take electric field as the parameter, which will be supplied across the two terminals, cathode and anode, now I say, for the bulk device made up of gallium arsenide. Now here also we take electric field intensity, electric field simply, and onto the vertical axis we take the representation of J. So if you know the current is the flow of charges. Basically electrons are the negatively charged carriers, so the direction of flow of electrons we take reverse to the flow of current there. And with respect to the point, with respect to the surface area, or with respect to the line, we can define the current densities. So accordingly, we can represent the current density. Basically, we take current density represented by K bar, a vector quantity, which is measured in terms of ampere per meter. So this is measured with respect to the cross-sectional length here. On the other hand, we have the cross-sectional current density can be represented in vector form by J bar, measured in terms of ampere per meter square. So here we can say that a JE curve for the voltage control mode of operation, and again JE curve for current control mode, where J represents the cross-sectional current density, E represents the electric field. So this has been for the two modes here. Basically J as measured into the ampere per meter square, E measured into the volts per meter. So here the current with respect to the volt, so the current voltage or voltage current characteristic, VI characteristics of operation of the device, we can consider these to be the graphs. Now when we are working with the voltage control mode, so that time there it is the production of high field domains. So in the accompanying diagram, I can show you if we are working this particular bulk material operated with the electric field E. So on this particular left hand side, there it will be first of all the low field, and after that there it will be the high field. We consider that from left hand side to right hand side we have applied the electric field. So bar I give for a direction here. So electric field is applied, and here the shaded portion we can say that it is high field domain. So this is for the voltage control mode. Now when we associate it with the current control mode, so that time there it will be the production of high current. So this is the representation of high current in the shaded form, and in this particular region we can say that it is low current, and this we can give as a nomenclature to this diagram. It is high current filament. So both are provided with the application of electric field. So the rectangular cases shows you the bulk material of either gallium arsenide, indium phosphide, or the cadmium telluride. Here the high field domain that has been shaded here is having the plane that is perpendicular to the direction of the electric field, and these plane go along that particular direction from left hand side to that of the right hand side, leaving back the low field and along with the high field. Whereas into the current control mode we have the electric field applied, and there it is the production of high current element. This is the shaded portion, high current element, and that is aligned towards the direction of the current here. Now as we want the bulk to exhibit the negative resistance so that it can be worked for the purpose of microwave energy generation, the mathematical representation of negative resistance can be with the form of ratio. The ratio will be for differential current represented as dI to that of the differential voltage, here we can represent dV. In terms of the current density and the electric field, here we can replace a dI by dJ. Here J is the cross sectional current density, and dV we can replace by electric field, so this it will be dE here, and this particular ratio is supposed to give us the negative resistance curvature. So I write here negative resistance. Now as we have gone through the two modes here, voltage control mode and current control mode, so for both the modes we again take the axis representing the J, that is cross sectional current density, versus the electric field E here, and we can mark different values so that we can exhibit there in the curvature of the negative resistance. So here onto the left hand side we have here voltage controlled mode, whereas onto the right hand side we shall be explaining current control mode. So here we again take electric field E on the horizontal axis and the cross sectional current density J onto the vertical axis. As we go on increasing the electric field into the voltage controlled mode, we come to know that as electric field increases, the current density also increases, but after a certain threshold point. So here we can write ETH. In the previous video also I have formulated ETH according to the findings of the JB Gunn here. There it is a drop down into the drift velocity of the electrons, finally resulting into the reduced current. The current reduction means reduction into the current density also. So this is the curvature that shows you a negative resistance. On this curvature, if you take the center point for this particular slope here, we can mark this is the value of E suffix 0 here. let us say this is the marking of E suffix 1, and let us say this is the marking of E suffix 2 here. Similarly, onto the vertical axis, we can make the markings of J suffix 0 across the marking of E suffix 0. We can obtain J suffix 1 across the marking of E suffix 1, and then J suffix 2 across the marking of E suffix 2 here. So this is for the voltage control mode. So I can say that exactly when the electric field is increased from E1 to that of E2, there it is the exhibition of negative resistance as the current density is dropped from J1 to J2. So we start at 0 here. So onto this particular axis, 0, 1, 2, 3, 4, this way, the magnitude of current density in terms of ampere per meter square is to increase here. But though E1 is increasing up to E2, J1 is decreasing up to J2. This is the negative resistance I write here. So this was into the voltage control mode. Now into the current control mode. Here we can have the marking of E0, then E1, then we have E2 here, and this can be the marking of ETH. And correspondingly across with respect to E0 we can have J0, with respect to J1 we have E1 here marked already, and with respect to J2 we have already marked E2 here. So as we increase here electric field here, for current control mode also we find if we increase E1 to E2, there it is decrease from J1 to J2, that is again a negative resistance. So this was all about the differential negative resistance. We have also shown the mathematical formulation in very simple form. Now let us come to our main topic where we shall be learning what exactly the two value model is there explained by Ridley, Watkins and Hilsum. Now to explain the two value model according to the Ridley, Watkins and Hilsum, we take the help of representing the energy bands here. We can also call this to be the energy band diagram. So here in this particular diagram, we have very first of all the valence band, and next to the valence band there it is the very important conduction band, and in between the conduction band and the valence band there it is a gap, and the gap is called as forbidden energy gap or simply forbidden band. But basically there are only two energy bands associated. So this is the valence band and this is the conduction band. Once the charge carrier is shifted from valence band to the conduction band, it will be supposed to be free to move inside the bulk there, producing or constituting the current here. So initially it is very essential that whatever the electrons are there associated with the atoms, molecules there, with respect to whatever the bonding that particular structure is supposed to be present there, it has to shift from valence band to that of the conduction band, and inside the conduction band the exact operation of our typical Gunn diode we shall be discussing onto the gallium arsenide n-type semiconductor material here. Now here the valence band can be represented here at this particular marking. We have K here marked for the valence band, and after a forbidden energy gap, the forbidden energy gap has to be of the value represented E suffix G here by 1.43 in terms of electron volts here. Now after that we come to this particular level, that is starting of the conduction band here. In the conduction band there are representation of these two values. So to this particular valley we can name lower valley, and the another one that is represented at somewhat more energy as per as the energy band diagram is concerned can be called as upper valley. Now, what is the energy difference between the lower valley and the upper valley? The energy difference between these two valleys can be represented into the diagram by delta E, and the delta E is having the value 0.36 electron volt here. Now, there are two energy differences inside this particular diagram. Initially, all the electrons shown with the solid black dots are inside the valence band. They have to get the energy amount of 1.43 electron volts, then they will be capable to get shifted into the conduction band, and when they will be in the conduction band, they will be first of all occupying the place inside the lower valley. After they get again energy by 0.36 electron volt, they will be shifted to the upper valley, and this shift of electron from lower valley to the upper valley, that completely is explained by the Gunn effect that we have already covered here. Now, when the electron is having a position inside the lower valley, so that time the mass of the electron can be represented as m suffix el, and it has the value 0.068, whereas the mobility of the electron can be represented as mu suffix l, and it has the value 8000 in terms of SI system of units here. Now, when the electron occupies a place into the upper valley, so that time the mass of the electron can be represented as m suffix eu, and it has the value 1.2 into the standard units MKS system or SI system of units, whereas the mobility can be represented as mu suffix u. So this is equal to 180 here. Now, here in this diagram, I have marked the values of the masses of electrons and the corresponding mobilities of the electrons belonging to the lower and upper valleys. If you observe, when according to the Gunn effect, whatever the operation we have studied to exhibit the negative resistance when the electron gets shifted from lower valley to the upper valley, so that time there it is a change into the mass as well as the mobility. Initially the mass is shown to have 0.068, now it will become 1.2. So this is a direct increase into mass of the electron. Whereas if you look at the mobility value in the lower valley is 8000. Now when it gets shifted to the upper value, the value is 180. So this is a direct decrease. So we can make a conclusion or a statement here that when an electron shifts from lower valley to the upper valley, so in that case the mass of the electron increases and mobility of the electron decreases. Now we know that the current is constituted by the flow of the electron. So flow of the electron possesses good mobility. When the mobility is decreased, it means that the flow of electrons has been slowed down. Therefore, it will be constituting a lower drift velocity into the electrons. Therefore, there it will be a lower current production, lower cross-sectional current density with respect to the bulk device, and finally we can have a negative slope onto the curvature for electric field versus the current density here. Now, with respect to the two valley model that we have shown, for the n-type gallium arsenide material, we can show the representation of the two valleys for mass and the mobilities in a table form. So here, very first of all, we name a valley here. Then we can have the effective mass. Next to that, it will be mobility and the energy separation. So here we have a lower valley that we can represent L valley, and upper valley can be represented as U valley. So here we have the mass 0.068 for the lower valley, mass of the electron in the upper valley that we have already shown into the diagram. 1.2, mobility of the electron in L value, that is 8000. It can also be expressed in terms of centimeters per volt second here, and here it is 180 centimeters square per volt second. Whereas in both the cases the energy separation can be denoted by delta E is equal to 0.36 electron volt for the lower value and delta E is equal to 0.36 electron volt for U value. So as we have gone through the understanding of the two value model, we have represented the mobilities and masses of the electron belonging to the lower value and the upper value. So as in the previous case, to see the differential negative resistance, we had the voltage controlled mode and the current controlled mode. Thereupon we had the graphs with respect to the increasing electric field, let us say E1 to E2, we got a drop down into the current density from J1 to J2 here. So to see how exactly the negative resistance occur according to the two value model, we have the three cases. So on to the left hand side we have the first case where we have capital E, that is less than EL. Now here E is less than EL, so the suffix L represents with respect to the lower value. Here the E is representing the energy, you can say, as it was supposed to be the energy band diagram. So we assume that the electrons have sufficient energy so that they can shift from valence band to the conduction band, and at the conduction band, very first of all, they occupy the places into the lower value. So here I represent L value and here it is U value representing the upper, and this is L value for lower here. On this axis we take the representation of capital E, the energy here, and on this axis you can take a distance parameter also, or we can represent simply K according to the previous diagram here. Here it will be the marking of the 0. So initially when E is less than EL, it has sufficient energy to get into the conduction band, so it will occupy the place into the L value. So here all the electrons have been occupied into the L value. No electron gets shifted from L value to U value provided the condition E is less than EL. Now the next case we can take with the help of this diagram, where we take the E has increased than EL. So here we take EL less than E here, but which is less than EU. So here we can take that capital E suffix L represents the energy level of the lower value, whereas E suffix U represents the energy level of the upper value. So again here we have L value and this is U value. So when the energy E has increased, so EL is less than E, but this E is less than EU. So on the same graph where we have K versus energy E, few of the electrons that were all inside the L value have got shifted to the U value. So I can say that when the energy increases greater than that of the energy level of lower value but less than that of the upper value, few of the electrons starts moving from lower value to the upper value. So this exactly we can say that transfer of the electrons from one value to the another value. Hence at the end we can call the devices that are working based on to these principles and this particular working, we can call the transferred electron devices. So this was the second case. Now at the third case we take the condition that is EU is less than E. So the energy of the electron when it is greater than the energy level of the upper value. So here it is the upper value. So this will be the energy level. On this axis we will take E, K here and 0 markings here. Now this is the L value. So this is the marking of EU. This is the marking of EL. This is for EL. This is EU. Right now we don't need here EU here. So when E is greater than EL as well as it is greater than EU in the third case. So all electrons have got shifted to the upper valley. So we can say that here it is the complete transfer of electrons from lower valley to that of the upper valley. So we can simply summarize that when EL is greater than E, no electron moves from lower to upper valley. When E is greater than EL but less than EU, few of the electrons starts moving from lower valley to upper valley, and when it increases so that it is greater than EL as well as EU, all the electrons have shifted to the upper valley from the lower valley. Now the behavior of the electron inside the gallium arsenide bulk taken as a typical condition that we have explained in the last figure here will definitely affect the conductivity into the material here. Basically, the conductivity is represented in the semiconductor physics. We take the symbol sigma here, and sigma is dependent on E in the bracket mu suffix L into N suffix L added with mu suffix U into N suffix U. So as earlier equation, if we treat to be equation number 1, I name it by equation number 2. Here mu suffix L and mu suffix U you are very well familiar as per the last figure. This is mobility of the electron in the lower valley, mobility of the electron in the upper valley. E represents the electronic charge, whereas N suffix L and N suffix U represent the charge concentration or the density. So how many number of electrons are there inside the lower valley, that is represented by N suffix L? How many electrons are there in the upper valley, that are represented by N suffix U? So this is the representation of conductivity. Conductivity into the N-type gallium arsenide can be denoted by sigma. So as we have given this equation number 2, next to represent the negative resistance as like the equation number 1, we shall be taking a differentiation. So the differentiation of sigma will be with respect to the capital E. Therefore, we express d sigma by dE, and it will be getting the form onto the right hand side. E, small e, the electronic charge in the bracket. Here we have mu L dNL divided by dE added with mu U dNU divided by dE, and the second term will be added. It has again the electronic charge outside, NL. So here we have the second term, E in the bracket N suffix L in multiplication to d of mu suffix L divided by dE added with N suffix U into differential of mu suffix U with respect to E here. So let this will be equation number 3 here. Now if we consider that the total density of the electrons, either it may be the lower valley or the upper valley, we can express N is equal to simply the addition of NL with NU, and also the mobilities mu suffix L and mu suffix U are proportional to capital E to the power P, where P is any constant. So in that case we can express the differential equation as d of in the bracket NL plus NU, the total concentration or the total density of electrons with respect to E here, equal to, now we can say it will be dN by dE simply by this relation, and this will be equal to 0. So therefore we can write dNL by dE is equal to minus dNU by dE here. So if this equation is given, the next equation number 4, we have to give this equation number 5 here. Now with these two relations, we can also express d mu by dE proportional to d e to the power p divided by dE is equal to p in multiplication to capital E to the power small p minus 1. This will be equal to small p e to the power p divided by capital E in proportional to p mu divided by E, and finally we can express it is equal to mu into small p by capital E. Let this will be the next equation number 6. Now we can make the substitution from equation number 4, and equation number 6 can be resulted into the equation number 3, giving us d sigma by dE equal to E in the bracket mu L minus mu U into d suffix NL divided by d suffix E here, added with E in the bracket NL into mu L added with Nu into mu U into P divided by capital E. So this is equation number 7. Now, as we know, the Ohm's law can also be expressed by using the current density and the electric field. Basically, the Ohm's law is equal to V given in terms of I into R here. So in terms of I replaced by the current density J, voltage replaced by electric field intensity E, we can have the relation J is equal to sigma E. So as R represents resistance in terms of ohms, sigma represents conductivity in terms of mho. So reversal of resistance. So according to this Ohm's law equation, we can express dJ by dE equal to sigma added with the ratio of d sigma by dE into capital E. So let this will be the equation number 8. Now equation number 8 can be rewritten in the form 1 upon sigma dJ by dE equal to 1 plus d sigma by dE divided by sigma divided by E here. So this can be the new equation, equation number 9. Now to look at all these particular formulation, up till now we have gone through, the condition of the negative resistance can be expressed by the next equation, and here we take a negation of the ratio of, here we have the numerator represented by d sigma by dE and the denominator represented by sigma by E here, so that can be greater than 1. So this equation is very, very important. This is the condition of negative resistance. I give it equation number 10. Now we can make substitution of the equation number 2, and along with the representation of F as the ratio of Nu by NL here. So the concentration into the upper valley for electrons divided by concentration of electrons into the lower valley will give us the frequency of oscillation. How many electrons have shifted from lower valley to the upper valley? So that will decide the oscillation frequency, and taking into the consideration of F, the frequency here, we can express the oscillation condition as mu L minus mu U divided by mu L added with mu U into F. This is one bracket in multiplication to minus, here we have capital E divided by NL and dNL by dA minus P. So this can be greater than 1. So let this will be the equation number 11. So here we have expressed the condition of negative resistance in terms of only the sigma E and the differential of the two here. Whereas here we have represented by taking the help of mobilities also and the concentrations also, along with the constant P here. Now the current density, cross-sectional current density J bar in the magnitude simply J can be expressed as Q into N into V here, where Q will be equal to electric charge. That we can also represent by small e. Small n is equal to the electron density or concentration of electrons. So I mention here electron density. And small v can be represented as average electron velocity. So this can be given as equation number 12 here. Now if we take the differential of the equation number 12, we can represent dJ by dE is equal to here the electric charge Q into N, and here it will be dV by dE. This can be the equation number 13 here. Now here, as Q is the electric charge, it has the very constant value for electric charge in terms of coulombs. N will be the density of the electrons. So total number of electrons. So here it has not been splitted into the number of electrons or density of electrons into the lower valley and upper valley. It has a complete concentration of free electrons into the conduction band. So these two are constants. Therefore, the differential with respect to capital E will be applicable to only the velocity here. The velocity of the electron, as we have already seen into the Gunn effect, is going to decrease after the threshold value of electric field has been crossed in terms of kilovolts per centimeter here. Therefore, we got this new equation, equation number 13. Now, the condition of negative differential if we take, so it can be converged, and finally we shall be writing d of the velocity, we can represent the drift velocity divided by dE. So differential of velocity will be the dVd divided by dE. It will be equal to mu suffix n and can be less than equal to 0 here, less than 0. So this can be equation number 14. Here the representation of suffix n to the mu. So mu is with respect to all the electrons inside the bulk device. So here mu suffix n denotes the negative mobility of the electron. So here I write negative mobility of the electron. Now to see the negative mobility of the electron, the drift velocity will be reduced, and finally the device operation will be there. The negative resistance will finally lead to the energy generation in the microwave form. So as for any electronic device, we take the characteristic in the form of voltage versus current. For the Gunn diode working as oscillator using the working of operation according to this two-valley model RWH theory, we get a curvature with respect to, here we have electric field intensity onto the horizontal axis, the cross-sectional current density J onto the vertical axis. So these will be the zero markings. So as we call voltage current characteristic for any electronic devices VI characteristics, we can call this to be the JE characteristics of Gunn diode. So in these characteristics, we initially have increase into the E that will result into increase into the J here. So here linearly increasing current density with respect to increase into the E here will be up to it attains the level of the lower valley. So here I mark EL. Up to there it was a linear increase here. After that, we suppose according to the two valley model, the electron have occupied the space into the lower valley, and this curvature can go from this place to this place. After this place, the electric field is again increasing, the energy associated with the electrons is again increasing, so that there it will be a start of the electron to shift the value from L valley to the U valley. So therefore at this particular place I can mark the threshold value that I represent E suffix TH, after which there it is the actual shift here. So the electrons are getting shifted to the upper valley, so there it will be a drop down. As we have seen into the two valley model, the mass of the electron increases and the mobility decreases. Due to the decrease into the mobility, there it will be a drop down in the current constituted here. So this will be up to, we have here the energy EV represented here, and finally for the upper valley we can represent EU here. So now all the electrons have got shifted from lower valley to the upper valley. So this region that has resulted into the reduction of current density, we can say this is the negative resistance region. And whatever this dashed line has been shown, which has not been included any drop down of negative curvature, this is the original bulk resistance value or resistance curvature, we can say. So if it is not operated along this particular electric field of the threshold value, it would show the original resistance values. So here this is, I say, is the valley point, and for the valley point we have the valley electric potential or electric field represented. The corresponding value of the current density we can denote by JV here. Whereas for the threshold value of electric field, we have the threshold value of current density here denoted by J suffix TH. So I name here current density in terms of ampere per meter square, and here it is the electric field. And finally, after this particular position, that is the negative resistance region has been gone through, we have the ultimate bulk resistance. So as we have shown you the characteristics of the Gunn diode according to the Gunn effect and the RWH theory, with the two axes representing the electric field and the cross-sectional current density, we can also show you the same behavior of the device by taking one axis again onto the electric field and another axis representing the drift velocity. So we come to this graph. Onto the horizontal axis we mark E here. This is our electric field, and this electric field is expressed in terms of kilovolts per centimeter here. Whereas onto the vertical axis, instead of cross-sectional current density, here we take the drift velocity. And the drift velocity can be denoted by V suffix D in terms of, here we have centimeter per second here. So this is the original curvature if it is not the exhibition of the negative resistance here. So here we start at 0, E increasing, the velocity of electron also increasing. So this relation can be given as the mu L, the mobility of the electron into the lower valley, in terms of the drift velocity divided by the energy level simply. Beyond that point, so I can say this is the EL marking, this is the ETH marking. After this threshold value, there it is the negative resistance, and for overall electrons, mu suffix n mobility can be represented as differential of the drift velocity Vd with respect to dE here. This will be the valley point, EV I mark. This will be the point of upper valley, EU, and from here we can have the relation of mu suffix u, mobility into the upper valley, is equal to the drift velocity Vd divided by capital E here. Now as J.B. Gunn has given a lot of experimentation with respect to the bulk devices exhibiting the gallium arsenide compound semiconductor or indium phosphide or the cadmium telluride, we have all these understandings. Now there are the theoretical values and the experimental values that has been observed with respect to this particular device. So here in the horizontal axis we have the electric field represented by E here in terms of kilovolts per centimeter here, and onto the vertical axis we can express the drift velocity denoted by V suffix d in terms of centimeter per second here. So this is the solid curvature representing the theoretical values, whereas the curvature with the dots has represented the experimental values. So there is a small change as we go on to the negative resistance curvature. So this was all about the RWH theory, Ridley Watkins Hilsum, and the two valley model. So by the next lecture, understanding all these particular concept, we shall be practicing problem number 1 based on to the Gunn diode. I hope you definitely get benefited by the knowledge we share for microwave engineering and for another subjects too. So for more information like this, you can subscribe to Ekeeda channel. Thank you.